Welcome to today's Explainer. We're jumping straight into the mechanics of scaling. Have you ever wondered what actually happens mathematically when you pinch and zoom on your screen or enlarge a digital image? It's not magic, it's geometry. Today, we're locking in on the grade 8 geometry principles that control exactly how proportions, perimeters, and areas behave when figures change size.
Real quick, here is our roadmap. 1. What are similar figures? 2. Scale factors and perimeters. 3. The squared area rule. And 4. A quick recap and a final challenge. We'll start with the basics of 1D perimeters, build up to the plot twist that is the squared area rule, and wrap up with a challenge that pushes your understanding into the next dimension.
All right, Section 1. What are similar figures? Let's make sure we're on the exact same page before we start changing any sizes.
When we talk about similar figures, just imagine taking a shape and zooming in or out. The overall shape doesn't warp or distort at all. The angles stay perfectly identical and the proportions are completely locked in. So if one side suddenly doubles in length, every other corresponding side has to double too. They are mathematically synchronized.
To measure that change, we use a multiplier, and we represent it with the lowercase letter k. You can think of k as the mathematical engine for this whole operation. If you're enlarging a shape, k is going to be greater than 1. If you're shrinking it, k is a fraction between 0 and 1. It is the absolute constant of proportionality that links your old figure to your new one. Everything hinges on k.
Moving on to Section 2, Scale Factors and Perimeters. Let's see what happens when we combine these individual side lengths to find the total distance around a shape.
Perimeter is what we call a one-dimensional measurement. Now, even though it wraps around a 2D shape, the perimeter itself is basically just a simple line segment bent at the corners. Because it's one-dimensional, the scaling relationship is incredibly direct. It's linear. If every single side gets multiplied by k, then the total sum of those sides, your perimeter, is also simply multiplied by k.
Let's do a quick pause check to make sure this is clicking. If a triangle's side lengths are tripled, meaning a scale factor of 3, what happens to its total perimeter? Go ahead and pause the explainer for a second if you want to think it through. The perimeter also triples. It perfectly illustrates that linear rule. Whatever happens to your 1D sides happens exactly to your 1D perimeter. Since the sides were tripled, k is 3, and we're just adding up those expanded sides. So the total distance around the triangle is exactly 3 times as long. It's a simple, elegant, and perfectly proportional relationship.
All right, Section 3, the squared area rule. This is where we leap from one-dimensional lines right into two-dimensional space. We're no longer just measuring the fence around the yard, we are measuring the grass inside. And this is where the math gets a fun plot twist.
If your instinct tells you that the area just multiplies by k, like the perimeter did, scratch that. The area actually scales by k squared. It's arguably the most common pitfall in geometry, but it makes total sense when you think about it. Area requires multiplying 2 dimensions together, right? Length times width. If you multiply the length by k, and you multiply the width by k, you're multiplying the total area by k times k, and k times k is k squared.
When you break down the math, the compounding becomes incredibly clear. If we take a square and double its sides, so k equals 2, the new area isn't just double, it becomes 4 times larger, because 2 squared is 4. And look what happens if you have a scale factor of 3. The area blows up to 9 times the size. Because you are scaling in both directions simultaneously, the growth compounds exponentially.
When you compare these rules directly, you really see the fundamental difference between scaling a one-dimensional boundary versus a two-dimensional space. Perimeter stays linear. Area gets squared. If you take absolutely nothing else away from this explainer, let this contrast be the one rule you memorize.
Time for pause check number 2. If you scale a rectangle's sides by a factor of 4, exactly how many times larger is the new area? Keep in mind what dimension we are working in, and pause the explainer if you need to run the numbers.
The area becomes 16 times larger. The crucial thing to remember is that because we multiply both the length and the width, our scale factor gets squared. A scale factor of 4 means our k is 4. Since area is 2D, we apply the squared rule, and 4 squared is 16. It's honestly kind of wild how quickly two-dimensional space expands compared to its one-dimensional borders.
Which brings us to Section 4, Recap and Final Challenge. You've navigated these dimensions like a pro today. We've scaled lines and we've scaled space. Let's lock it all in firmly before you go.
Here is your quick recap. Similar figures are strictly proportional. One-dimensional measurements, like your sides and your perimeters, scale linearly by a factor of k. But the moment you start measuring the inside space, your 2D area, you have to emphasize that squared relationship. You square the scale factor. Always ask yourself what dimension you're dealing with.
And that leads perfectly into our final transfer challenge. We know 1D scales by k, and we know 2D area scales by k squared. So, what do you think happens to the volume, a three-dimensional measurement, when a similar figure is scaled by k? I'm going to leave you to reason through that progression on your own. Keep applying these patterns, and I'll see you in the next explainer.